here. Today, it's a pleasure to welcome Elisa Bortolas. She's a postdoc at the University of Milan, Bicocca, and she got her PhD in astronomy at the University of Padua in 2019, working on dynamics of black holes nuclei with Michele Amatelli. She also won a very prestigious prize in Italy for her PhD thesis, the Gratton Prize. And before moving to Milan, she was a postdoc at the University of Zurich, working on black hole dynamics and dynamics of massive black hole binaries in the early universe. And today, she will talk about the path to coalescence of massive black hole binaries across time and space. Please.
Thank you so much, Fabio, for the very nice introduction. And thank you so much to all of you for spending some time here to listen to what I'm going to tell you today. And yeah, as Fabio already mentioned, what I'm focusing on in my research mainly is massive black hole binaries. And today I will try to bring you with me on a journey to really understand what are those objects, how they behave across the evolution of the universe. And so I'm starting this story from the very beginning, from the beginning of our universe. And actually, probably most of you are familiar already with the idea that galaxies, back in the day when they started forming at the beginning of the universe, they were tiny, they were much smaller than today. And they built up their mass and aggregated by repeated mergers. So here, what I'm showing you is an body simulation of cosmological simulation that basically shows you the formation of a galaxy that looks a bit like our Milky Way. And you see that galaxies are merging and forming larger and larger objects. And this is the first thing to keep in mind for us today. The second important thing that is probably very obvious to most of you is the fact that most galaxies host black holes in their center. And we do observe them in the present-day universe. We have this very beautiful image of the Event Horizon Telescope collaboration. I think part of the audience is working on that, actually. So thank you for this very nice result. And so we are more and more convinced of the fact that galaxies do harbor massive black holes. And actually, they don't do it just today in the universe that is close by, both in time and space, but also at the beginning of structure formation. In fact, it is pretty clear since almost 50 years that high redshift quasars are powered by the accretion of massive black holes. So we observe black holes of even 10 to the 9 solar masses shining at a redshift that is almost 8. So when the universe was very young, less than 1 billion years old. And so if we combine this idea of massive black holes being there since the beginning of the universe and galaxies merging, what we expect is that often during the evolution of our universe, two massive black holes will find themselves in the same galaxy merger remnant. And if they are lucky enough that some processes really have them shrinking down to small scales, at some point, the gravitational waves start taking over in their evolution and bring the two black holes to a merger. And so this is really the very beginning of what I want to tell you. But why do we really care about this? Well, what I'm showing you is the mass function of massive black holes as a function, of course, of their mass. And we see different realms. This is basically what we know from the present-day universe. At the low masses, we know that we have stellar black holes of 10 to roughly 100 solar masses, and stellar black holes are relatively well known in the sense that we know how they originated. They originated from the death of massive stars, and thus we observe them via LIGO and Virgo through the gravitational waves they emit when they are in binaries. But when we go to larger scales, so we talk about the massive black holes that I showed you before, that in this talk I'm going to very loosely define as anything above 100 solar masses, all the way up to basically 10 to the 11 solar masses. Well, those objects are way more mysterious. Are way more mysterious in the sense that we don't know really how they formed yet. We also don't know in detail what really enhanced their mass across the cosmic times, if it is gas accretion, the accretion of stars, the mergers of the black holes themselves, and also regarding those more massive objects, what we have is that they look like they are in a really symbiotic evolution with their host galaxies. In fact, there are some very tight relations that seem to connect the mass of those massive black holes with, for instance, the stellar mass of the galaxies in which they are found. And we don't really know in great detail what really makes those relations stand out. Actually, part of the audience here worked a lot on those very open issues. But what I want really to stress is that gravitational waves are going to be great tools to really shed light on those open questions. And the reason is the following. The reason is that what we are really missing in our understanding of the origin of massive black holes is the fact that we don't know much about their low mass end. So we really struggle to find massive black holes that are of the order of 10 to the 2 to roughly 10 to the 5 solar masses. Those are very elusive, and we cannot really observe them even in the very local universe. But those would be critical to find because it could constitute like the progenitors from which the more massive black holes we observe nowadays have grown. And we don't observe them in the present day universe, let alone in the farther away and more distant in time universe. But with gravitational wave emission and with the observatories that are going to detect gravitational waves from those black holes, we will encounter, we will go into a revolution because, for instance, the Lisa observatory that is planned to be launched in 15 years from now, roughly, is going to be able to detect the merger of massive black hole binaries between 10 to the 3 to nearly 10 to the 7 solar masses, not only in the present day universe, but in principle all the way up to redshift 20. So all the way up to the very beginning of our universe. And this is going to be amazing also because gravitational waves, on the contrary to normal, let's say, electromagnetic emission, they don't get absorbed. And so they can really travel undisturbed through the space and reach us, so that collecting those observations, we can really understand what the population of merging black holes looked like in the past. And so really starting from this point, one of the key things we want to understand to get ready to when the Lisa mission will be there and give us all this plentiful of information is to understand what is their path, the path to coalescence of the massive black holes. Because of course, we cannot be so naive to think that once the merger between two galaxies happens, also the two black holes will immediately merge. The two black holes need to go through different processes before they reach the gravitational wave-dominated regime. But before really going into this aspect, so really telling you all the details about the shrinking of the two massive black holes, I just want to briefly mention what we know today observationally, so not theoretically, about massive black hole binaries. So what can we observe already with our electromagnetic detectors? And what I'm showing you is that it gets harder and harder as the black holes get closer and closer. Because we do observe galaxies merging on the process of merger, and often we can distinguish the two separate nuclei of the galaxies, and sometimes we can find the signatures of AGN emission in both nuclei. So this is a signature of dual AGNs with in many, let's say in billion years even, may reach the gravitational wave-driven emission. And this can work out to the scales of, let's say, kiloparsecs. Recently, we have some detections at a few hundred parsec scales, but they are just starting to come forward. At smaller scales, when the two black holes are sort of bound in a, let's say, Keplerian binary, so they see each other, and their orbital period is of the order of million years, what we can do is to search for compact radio cores, because basically radio interferometry is the only possibility for us to solve parsec scales and really distinguish the two black holes. And with this technique, I would say we have the, let's say, most promising candidate massive black hole binary, which has been found by Rodriguez and collaborators and is at roughly 7 parsecs separation. And also radio observations are promising because we can observe the jets launched by the black holes. And if the black holes are two, we can see two misaligned jets in principle. As we go to even smaller scales, there is no telescope really that can help us distinguishing the two black holes separately. Maybe the Event Horizon telescope soon, but this you can tell me at some point, maybe. So what people does is to really go into spectroscopy and looks for binaries, for instance, at let's say a fraction of parsec scales, by looking at differences in the redshift of the broad and narrow line region. Because the broad line region is farther away from the black holes, while the narrow line, the gas emitting the broad line region is much closer. So that if there is a velocity shift between the two, this can be associated to the Keplerian orbital motion of the two black holes. And there are searches and several candidates that were found this way, but there are other explanations. Another possibility, when the two black holes get so bound that the orbital period of the binary is comparable to human time scales, so is of the order of years, is to look for oscillation, so periodic variability in their optical light curve. Why? Because when the two black holes orbit, they basically excite the massive stuff with the gas around them, and it is very intuitive to expect via many processes. I don't have time to go into the details of all of them, but the oscillation in the optical light curve is expected to be commensurate to the Keplerian period at which these binary orbits.
These are 10 to the 6 solar mass candidates.
Yeah, everything I'm showing here for reference is 10 to the 6, just because it's basically the sweet spot for these observations, but they can be adapted, of course, to larger or smaller masses. And now, when the orbital period of the binary gets to hours or even minutes, so we are really in the band at which Lisa is going to detect the two black holes via their gravitational wave emission. Here we are getting in the speculative regime because we only have predictions. And the idea is that, for instance, the two black holes may carve a cavity in the circumnuclear, the AGN disk that is surrounding them. So the multicolor emission of the AGN may be suppressed. So this could be a signature. Other possibilities is to look in the X-rays and look at modulations of the 6.4 keV iron emission line. And at the merger, so at the very moment of the merger, simulations predict that if there were two separate jets launched by the two black holes, those can basically align, get re-brightened, and also perhaps even we can have some neutrino emission, so a further messenger for our observation. And also the two black holes, once they merge, they can undergo a recoil, and this can really mess up the gas around and give rise to electromagnetic emission. But as I mentioned already, while the larger scale detections are kind of solid, the smaller scale really rely on assumptions and can have different interpretations. And at the even smaller scales, we don't have any like a strong candidate. And also, even just the theory to really understand what happens at those small scales is very challenging to work out because of the different physical processes at play. But so let's say that now we don't really care about the electromagnetic emission, but just want to figure out what happens in the journey of the two massive black holes as they are trying to meet each other, right? And the first paper, seminal paper that really looked into this problem has been put forward in the 80s by Begelman, Blanford, and Rees. And what they suggested is that, first of all, the two black holes will sink inside the common potential well of their host galaxy via dynamical friction, which is a sort of gravitational drag that really makes the two black holes lose energy until they meet in the center. At this point, the two black holes will become bound in a Keplerian binary, so they will see each other. And from this point onwards, since at this stage the two black holes aren't close enough for gravitational waves to really take over, they would shrink via stellar hardening. So each time a star gets close enough to the two black holes, it will interact with it, extract energy from the binary, and shrink further and further. Of course, at those scales, we can also have a disk of gas that can further impact the evolution. We will see something later on. And also can give rise, of course, to the electromagnetic counterparts. And until at roughly milliparsec scales, gravitational waves really drive the final coalescence. But this very simple and in a way, even a little bit naive picture was really challenged recently because in the last years or decades, better to say, people started working more and more on this problem, and what was initially a very simple evolutionary scheme became much messier. And so don't get scared about these messy plots. I'm going to guide you through the different processes, and we'll see something in the next slides. So first of all, let's start from the large scaling spiral. Before I mentioned that a black hole can lose energy and angular momentum via this dynamical friction. And basically, the idea here is, that was put forward by Chandrasekhar already in the 1943, is that basically the black hole will deflect stars via gravitational focusing, create an overdensity at the back of its trajectory, and so the black hole would get slowed down by this overdensity, and so lose energy and angular momentum, and slowly inspire towards the center. And this theory seems to work pretty well when we are looking at the galaxies we observe today. So for instance, giant ellipticals just made of stars and pretty much spherical. And in those systems, the theory basically gives us a very handy time scale, the dynamical friction time scale, with which we can really compute how much time a black hole would take to go from the farther scale down to the center. However, are we sure that this really works when we have a galaxy that is not so nice and smooth, but something that looks like something would happen in the early universe when galaxies used to look much messier? And here, what I'm showing you is an animation taken from a zoom-in cosmological simulation that I performed of black holes that were trying to inspire in a typical high redshift galaxy at redshift 7 to 6, when the universe was roughly 1 billion years old. And you will see a black hole in the center that we will consider the primary, and as an example, two other black holes that we will consider the secondary, that we will try to reach the center. Oh, sorry. Okay, here we go. And so in the beginning, the orbits are nice, but you will see immediately that the galaxy starts developing structures. It has sort of spiral arms, and then a bar, and then one black hole basically meets the other, but the other one in the same time scale is basically ejected outwards. So this is something that, of course, cannot be treated with time scale argument, right? And here is a more quantitative depiction of what happens. Here instead I'm showing a further black hole. So we have three black holes that initially basically had the same orbital properties, starting from nearly the same separation, but over the same time scale, two of them make it to the center, and one in the same time scale is not only doubling its initial separation from the primary black hole, but also doubling its initial angular momentum, meaning that it would stay farther for long. And so we asked ourselves together with my collaborators, so what's really going on? Why is the dynamical friction not working? And in order to really dig out the details, what we did is to compute the torque that the black holes that I'm showing here are experiencing as a function of time. And on the one side, we computed the dynamical friction-induced torque, so the dragging force, which is the red line that you see below in those plots. And also we computed the global torque, so the torque that is induced by all the mass that is present in the environment of the black hole. So the bar, the spirals, the fact that the galaxy undergoes some other galaxy flyby, everything. And you see here that the dynamical friction torque is so much smaller. This basically implies that in those messy environments, dynamical friction is not the dominant mechanism that really sets out what is the orbital spiral of those massive black holes. And even if this, what I'm presenting is just a specific work, it goes in the same direction of many other works that are popping up in the literature, some of which also involve, for instance, Angelo and Fabio, and really seem to suggest that the spiral may be very stochastic, especially in those high redshift galaxies. And so, just to add more on this stochasticity, what I'm showing here is the results from some other simulations taken basically in the group of Lucio Maier by Valentina Tamburello, who tried to understand what is the effect in the decay of massive black holes if the host galaxy has a massive star-forming giant clumps that are often observed in galaxies at redshift 3 to 1, let's say. And so those massive clumps can really act as scatterers for the black hole spiral and make it very random. And here you see the case of two black holes that initially try to decay in a dynamical friction fashion. And at some point, they encounter a clump and they basically get out of the disk and they would never come back. And here is basically the same concept, but instead of looking at the very large scale, here we are looking at the smaller scale at which we can have the circumnuclear disk of gas. That is a common structure that is expected to be present in many galaxies at scales of, let's say, 100 parsecs. And again, the star-forming clumps that can form in those disks can really make the spiral much more stochastic. So stochasticity here is my main point. But also, unfortunately, what I showed you so far are basically very expensive numerical simulations. Some of them really involve zoom-in cosmological simulations. Others are more like isolated galaxies. But overall, each simulation can take months to be completed. And this is a problem if we really want a statistics of what is the time scale for the black holes to really go to the center. So together with my colleagues, what we did is to try to think a workaround to really have a wider statistics and understand what is the spiral time scale. So for instance, the first thing we did is to try to generalize the prescription for dynamical friction that typically works well in a spherically symmetric isotropic system to galaxies that have multiple components, like a dark matter halo, a disk, a bulge, and are also rotating. And we set up a prescription that works pretty well in comparison to numerical simulations. And to these prescriptions, what we added as a first attempt is we added a bar. So we have here just a Milky Way-like galaxy with its components, and we put a Milky Way-like bar in the galaxy that is rotating. And then we try to put a black hole and make it decay in the host galaxy. And here are, as an example, two different cases of the orbit in which the black hole has exactly the same initial orbit, but in one case, the galaxy has no bar, and in the other case, the galaxy has a bar. And you see immediately that in the barred case, the decay is much more messy. It's not regular as here. But also in the barred case, for instance, in this situation, the black hole reaches the center in 10 gigayears, while here it would take more than a Hubble time. So already we don't really need the very messy environments. Just the effect of a bar can make the inspiral stochastic. And also here, to stress further this point, what I'm showing you is the inspiral time scale of black holes that were put at different initial orbital phases compared to the direction of the bar. So here, the black hole is basically initially on the bar, while as we move, it gets to 90 degrees and so forth. And the time scale for its inspiral, while without the bar here would take more than a Hubble time, with the bar, in most cases, it makes it to the center. And here, I'm showing you an analogous case in which without the bar, it would take 12 billion years. With the bar, it takes 9 to even like something like 5 billion years. And in one case, it never makes it to the center. So again, just a bar-like structure can make the spiral very
I have a question.
Yes, please.
So is it important that the bar should be rotating? If it is static, presumably you won't find this. Is that correct?
Yes, I believe so. I think that, of course, the inspiral will take a different time, even if the bar is standing. But the main thing here is basically the kicks that the rotating bar is giving to the black hole that basically counteract dynamical friction in some situations.
So have you tried different rotation rates for the bar to see what it does?
Well, here not really, because we just focused on a bar that had exactly the same properties as the one measured for the Milky Way. Yeah. But it's of course a good point. I expect that as the bar rotates faster, this effect would be more important actually. But it's definitely a good point. And also
saying that they are co-rotating or counter-rotating.
Yeah, okay, so we tested that. In the case of co-rotation, the effect of the bar is more important because the relative velocity between the bar and the black hole is smaller, while in the counter-rotating case, the relative velocity gets larger, so that basically it is like as if the effect of the bar was averaged over the rotation of the black hole, and the bar is not as important anymore. So definitely the co-rotating case is the more important for the stochasticity, if it makes sense.
Yeah, just very quickly, I was imagining that if they are counter-rotating, it could be that the black hole comes and they're just like in the opposite direction, they just kick them out. Could that be possible? Any kind of like ejections coming from this situation or not?
Well, in the counter-rotating case, we don't really see anything like that. Also, because really you need the bar to interact for enough time with the massive black hole to affect it. While if the black hole is very fast passing through the bar, you don't really have an effect. What we see instead is that in the co-rotating scenario, in some cases, the black hole is basically never inspiraling because the torque of the bar counteracts completely dynamical friction, and the black hole stalls at close to the outer limb bundle resonance of the bar. Okay, so
Elisa,
yes.
there is a question online
Yes.
actually. Magda was asking, is there a resonant effect if the bar rotates in resonance with the binary?
Well, here I'm not really talking about a binary that is formed. I'm talking about a black hole that is coming from farther away and trying to inspire to the center. So the second black hole basically is as if it were not there, in the sense that it doesn't impact the decay of the other. So, and I would say that when the binary is formed, I don't expect a dramatic impact of the bar because this is on much larger scales and the separation of the binary is incredibly smaller when the binary is Keplerian compared to the scale of the bar itself. So I wouldn't expect anything like that. I hope I answered the question. Okay, so just very shortly here, I want to mention that we are working on this semi-analytical integrator, of which I already showed you some results, to implement further prescriptions. So for instance, the effect of giant clumps that I mentioned before, this is a work in preparation. The fact that the host galaxy would undergo cosmic growth, so it would increase its dark matter mass, and also it will puff up its disk perhaps and grow a bulge. And also with a PhD student in Milano, Bicocca, we are working on really making more effective the prescription for the stripping of the galaxy that initially hosted the black hole that is delivered in a bigger galaxy. And this stripping has been worked out typically in systems that were spherically symmetric, and we are working on generalizing really this prescription for systems that instead can have a disk or also multiple components. And so I think here I am basically finishing the first part of this presentation, and I really hope I pass the message that the spiral of massive black holes at large scales, even if in the beginning it was expected to be very easy to model, it's in fact very stochastic, and we need to do a lot more work to really understand what happens at those large scales. Yes.
This is very interesting. You showed an example where one of the supermassive black holes is ejected.
Yes.
How often does that happen in the simulations, and does that affect the counts of individual supermassive black holes that are existing?
Well, okay. So basically here, what I showed here is the resulting with, of running, which we explored the spiral of only 5 black holes, and 1 out of 5 got ejected. But of course, it's very low number statistics. I wouldn't say we can really make big conclusions with these. To make a more detailed studies, it's actually what we plan to do in this semi-analytical orbital integrator that we are trying to develop more and more. So eventually, we really hope to have a huge statistics and also have an answer, specific answer for this. But for now, I can only say that 1 out of 5 was ejected in the run ahead. If it makes sense.
Okay. I'd expect you to see those around, right? 20% of black holes being ejected.
Well, but when they leave the galaxy and they stay wandering far away, it's not easy to see them because it's likely they won't have much gas around. So it's very hard. Those are dark objects. Unless they do something fancy, like they eat a star, they found some big clump of gas that they may manage to eat it. But I would say it's not a probable thing to happen. So it's very hard to find those objects. Okay, and so let's go very quickly to the small scale evolution. So let's say that the 2 black holes really managed to survive all those things that try to defer their spiral and meet each other in the center of the galaxy. So the general consensus is that the 2 black holes would shrink via stellar interaction. So basically, I mentioned before, each time a star gets close to the binary, we have an interaction, and the binary shrinks while it ejects the star that got close. And actually, we need a large number of stars to bring the 2 black holes from the separation, the initial separation at which the dynamical friction is no longer efficient, all the way down to gravitational waves of the order of the mass of the binary itself. And actually, people started questioning throughout the years whether this effect was efficient enough to really drive, to ferry the 2 black holes down to the gravitational wave emission state. And in the beginning, it seemed like it was not possible. So it seemed like that the 2 black holes would stall at a parsec scale, because at some point the stars were no longer funded towards the center and the binary could not shrink anymore. And so people, including myself actually, we tried to set up solutions for this so-called final parsec problem, which would imply that all binaries would stay there forever, while instead we tend to observe only single black holes. not two of them. So this was an inconsistency between our theory and our results. So, of course, what you can expect as a solution to this final parsec problem, which is very general, is the fact that as the two black holes are stalled there can be a third galaxy merger, bringing in a third black hole. We can have a triple interaction in which typically two of the three black holes can easily merge, and maybe the fourth gets even ejected far away from the galaxy. Other possibilities that there can be objects like giant clusters of stars that go close to the binary, interact with it, and bring new stars to make it shrink further. Also, the fact that the galaxy is rotating appears to help the binary shrinking and this evolution. Also, people initially started putting forward the idea that a disk of gas could torque the two members of the binary in the right direction to make them shrink. And so this was the initial idea to solve this so-called final parsec problem. Actually, as people worked more and more on this problem, in the end, it was solved basically by itself, in the sense that it eventually became clear that the fact that the binary was stalling was just a result of the simulations that initially tried to study this problem and put the two black holes in a spherically symmetric isotropic galaxy. And in this potential, the only allowed types of orbits are Rosetta orbits. And basically, they conserve energy and angular momentum. And once you have ejected all the stars close to the center, you have no way to bring new stars to the binary and make it shrink in this kind of spherical potential. But in fact, we know that there is no galaxy that is perfectly spherical and isotropic. And all galaxies look much more triaxial. They have deviations from symmetry. And in those triaxial galaxies, the allowed families of orbits are much more varied. And the star that spends a lot of time far away from the center may eventually reach the center. And in this kind of galaxies, basically the families of stars allowed can sustain the shrinking of the binary all the way down to the milliparsec scale, at which we can have a gravitational wave emission. So the final parsec problem was solved in this very simple and natural way. And in the meantime, what happens, however, is that what initially seemed to be a process that helped the binary shrinking became a process that could make it expand. Namely, the fact that the binary can have a gaseous disk around it. And so the initial simulations supported the idea that the gaseous disk would shrink the binary, but more recently, actually in the very recent years, people started finding that depending on the properties of the disk and of the binary, in some cases, the disk itself would expand the binary. This is something we may not like if we want the binary to merge. And so it's worth definitely understanding better what's going on. What we did here is just to put forward a very simple argument, because basically most people working on this topic either study the evolution of binaries in a stellar background, so what I told you before, or they put the binaries in a disk of gas without stars. So we were like, but the two can exist together. They would exist together in most times. So we put together the evolution via stellar hardening and also via gas. And we put the most extreme and pessimistic scenario in which the gas disk always expands the binary. And we combined in a semi-analytical model the different prescriptions that describe the evolution of the binary. So the stellar hardening, the gas evolution, and at some point the gravitational wave emission. And first of all, I want to mention that the gas-driven expansion, we found it only to play a role when the binary was accreting a lot. Because basically, if here we have the binary semi-major axis, logarithmic, and how fast the binary semi-major axis shrinks, First of all, coming from the larger scale, the binary would undergo stellar hardening that is initially very efficient, but its efficiency gets less and less. And at some point, the gravitational waves can become important, and they are like a runaway process because they scale, they are a very stick function of the binary semi-major axis. And depending on what is the normalization in the effect of the gaseous disk, the gas can either be always subdominant or at some point become important. And our results here basically show us that the binary should always accrete at more than 10% of its Eddington limit for the gas to play a role. So since most binaries accrete at a much higher rate, a much lower rate, sorry, at 1% or even lower, this by itself is already telling us that it's not something very common. Also, the binary, if it manages to expand because it accretes a lot, it cannot expand forever to megaparsec distance, right? At some point, it would stop. And it is very natural to assume that it will stop its expansion at the self-gravitating radius of the gaseous disk, because this is a radius at which the people who found the expansion, basically the assumptions they made started breaking down. So we just stopped the expansion at this typical scale. And already putting in this further ingredient, we were able to say that binaries could never expand if their mass is above 10 to the 8 solar masses. But let's say that we have a low mass binary that is accreting a lot. And so what it happens is, for instance, an example you can show here. For instance, the gray is the binary when there is no gas. If we put a little bit of gas accretion, then the binary may have some delay in its spiral, but still make it without an expansion. If we put the binary evolving at an Eddington ratio close to 1, which is the orange curve, the binary would expand. At some point, the gas expansion would become dominant. The binary would start expanding up to the self-gravitating radius, which is this line here, and continue stalling on the self-gravitating radius. However, in the same time the binary is stalling here, it's also growing a lot because it's accreting at Eddington. So its mass eventually becomes so large that for its stalling radius, gravitational waves become so efficient that they bring it to coalescence. And the funny thing is that if you put a binary that is accreting at a rate that is even super Eddington, everything happens in the same fashion, but faster, because the binary is accreting faster. So the in spiral time gets lower. And this, you can see it very easily in this plotting, which as the function of the Eddington accretion ratio, I show the spiral time of the binary for different masses. So in the beginning, we have the nominal time scale, in which we only assume stellar hardening at gravitational waves. Close to the Eddington limit, we have a maximum time scale for the spiral, which is basically this configuration, the orange line I showed you before. And at some point, the spiral time drops again, just because even the binary is accreting so fast that everything happens super fast. And here I am basically at the end of this presentation. And I just want to briefly mention some key messages I really want to pass you. So first of all, the formation and the evolution of massive black hole binaries is not a straightforward process. It's not something that we can easily solve with pen and paper in 2 minutes. And really depends on the environment, on the properties of the galaxy in which those two black holes are trying to find each other. So this is a very important message. Also, funnily enough, what initially was thought to be the most naive part in the spiral of binaries, so the large-scale dynamical friction in spiral, is now what we see to be the most problematic, because we can have bars, spirals, scatters, everything. instead, what in the beginning seemed to be a problem, so the final parsec problem is now solved. And even if gas expansion can occur, it won't it would not prevent binaries from merging. And finally, what I think is the most important thing is that we need more work. So if you are interested in massive black hole binaries, I think we still have plenty of things to do before, for instance, the LISA Observatory will be out there and tell us something about massive black hole binaries. And here I stop my presentation, and I thank you so much for listening to here.
Thank you, Elisa. Questions? Ramesh.
Yeah, so this business about gas is causing the binary to expand,
Yes,
right? I mean, it was a shock when that result was first announced,
yes.
and I didn't believe it. But I thought after that, further work has shown that this will happen only in very special cases. Most of the time, actually, it does shrink. Is that the current situation, or has there been further development?
So it is definitely true that it needs some special conditions. So for instance, the binary should be nearly equal mass, first of all. It seems like the gas disk should be pretty thick and thicker than what is typically considered to be for AGN disks. So this could be already a hint of the fact that in most realistic situations, this does not happen. But I really think that here the problem is that basically, if you make a simulation of binaries in spiraling with one code, you get one result. If you change your code, you get another result, which is a borderline of a resolution issue. So I think really we are on the edge of being able to resolve properly this phenomenon, but we are not yet there. So I know there is a huge effort also from a community working on this to do a code comparison project to really understand what are the differences and why there is this phenomenology. But so I would say it's still an open problem, and it's not very clear how much simulations are ready to really solve this.
And your point is it doesn't matter.
Yes, exactly.
That was the other side. Even
Exactly.
if it goes out, it's still going to work.
Yeah.
Very interesting.
Yeah, in a way, according to those results, the expansion could even be a promising thing because it would just mean that the binaries that are creeping a lot spend more time in the electromagnetic band. So we may have a higher chances to observe them. So in a way, it could be even a good news. And in any case, mergers still happen. So we are all happy.
I was sleeping.
Yeah, great one.
Thank you.
And I was wondering also on this point where you showed that it's stalled at some point. Like two questions. You just mentioned about the mass ratios. Maybe in all your plots using equal mass ratios.
Yes.
How much does that have an effect also on the other processes involved? And I was a little confused as to where they exactly stalled and what that depended on.
Okay, so first of all, about the mass ratio. So the mass ratio, basically the expansion is only observed for mass ratios close to 1. Even if I put 0.1 mass ratio, the point is that the secondary spends more time farther away from the center. So it accretes more mass because it's closer to the gaseous disk. So I tried some experiments with different mass ratios, and the secondary would very quickly get to the mass of the primary. So this was basically something that didn't really impact the results, and that's why I only showed this part. And the second question, sorry, was about
you explained it, but where did it exactly stall? I just missed it, I think.
So the self-gravitating radius. So when you have a disk of gas around a black hole, what you have is that above a certain radius, you expect the gas not to be, let's say, in equilibrium between gravity, pressure, and so forth. So it would start developing structures like spirals, and at some point to fragment and form stars, actually. And in those situations where you start having spirals and then fragment, of course, all these phenomenology would break down because you are in a different configuration, and there is no work that suggests that binary can expand in the self-gravitating regime. That's why I stopped the expansion there. Also, of course, you can, I naively believe that you would have nearly the same phenomenology if you would just allow the binary to expand up to the typical radius at which you assume you have no longer gas, because the gas cannot be there at all scales, right? So this is kind of a parameter we can play around, but still I believe it kind of makes sense to fix this.
So cosmological simulations can resolve these kiloparsec scale messes, and we often write the caveat that, well, we don't account for stellar hardening, but it seems like the work you've shown has showed that this really doesn't matter in comparison to kiloparsec scale delays. So when it comes to predicting merger events, should we just be happier with what cosmological simulations predict?
Well, okay, this is a very interesting question. My message here, I would say that my thoughts, my personal thoughts, is that the critical point is stochasticity. So it may be that the two black holes will take a long time to spiral to the center due to those messy things. But in other cases, it may be that it takes 1/10 of what you would infer via dynamical friction. So it can be shorter or longer. So at that point, you are not really sure whether the smaller scale evolution takes longer or shorter. It's really a matter of how much it takes, because here, of course, you can have cases in which it takes even almost a Hubble time. In those cases, you can possibly neglect the small scale spiral, but it won't be true always. So I still think combining different things is really system dependent. And if you have a very steep density nucleus, probably the stellar hardening is going to be negligible. But instead, if the nucleus is not so dense, maybe not. So I would say that really we have to look at galaxies and decide depending on their properties.
So bottom line, does this help you at least? Are you going to get more mergers or fewer mergers?
With this, you mean?
Or with the new considerations of with all of this, some things throw out black holes, some slow them down and bring them in. On balance, is this good news for the project?
That's a great question. I wouldn't say it's good news in the sense that it's much harder to model the process. So it's much harder to have a good estimate of the merger rates of those objects. I still believe, I mean, it's not that we don't have to think Lisa will see black holes, because some of them definitely spiral. Just we have to really account for this stochasticity and to make new models to really take that into account without making a simulation for each case, right? So that's my idea. If I may add on this, actually, I believe that when you have major mergers, so two similar mass galaxies meeting each other, in this situation, the dynamical friction time, so the spiral time at large scales is pretty prompt in most cases. So at least for major mergers, I would be optimistic. For the minor ones, it's very tricky. Yeah.
Sure. Yeah. And
So I was going to ask you a two-part question. The first part was Peter's question, and maybe I'll just change it by saying, what do you think the uncertainty is in these merger rates? So what is the range of merger? And the second part of the question is, you had a great slide about electromagnetic counterparts, and you can see them as they come together with radio interferometry and the optical periodicity. Given the expected rates for what you might see with Lisa, are we seeing enough electromagnetic counterparts? Are we seeing enough hints of binaries in the optical or the radio that match the anticipated rate?
Okay, so regarding your first question, I mean, I think that the semi-analytical models that try to infer these merger rates are, I mean, we have a very broad range of merger rates going from a few up to hundreds. I would say that probably the most reasonable are of like tens of events over the LISA mission. Still, I mean, if you want to,
Tens of events
yeah,
over the whole mission.
over, well, a whole mission or not, it can be over 1 year or 3 years. It doesn't change much because it's really hand wavy.
Wow.
It's a very, I mean, even without adding this complication of, you know, those large scale in spiral possibly being very messy, already the merger rates are extremely uncertain. That's why we are not yet there to add those ingredients. We are working on that. So I cannot really give you right now what are going to be, how the merger rates are going to change even those processes, because they were like kind of just discovered. So we really need to work more on this. And regarding the binaries that instead are observed and if they are compatible with merger rates and so forth, I would say that, I mean, I'm possibly not the most expert regarding those observations. On the other hand, I think that at least at a large scales, we are happy because, I mean, in the end, the large scale is easy to observe. We have our cosmological simulations that pretty well reproduce what we observe outside. So in this stage, I would say we are happy. Instead, at smaller scales, it's really, really hard to make statements because, for instance, this observation we have only for one galaxy. And so it's one. I mean, we don't have a lot of statistics. And when we go into those methods for which we have many more candidates, I would say that most of them can be continuously disproved. And actually, there is a whole history of candidate binaries put forward in the literature and systematically being disproved after a few years with new observations. Also because, especially if you rely on those modulations in the light curve, unless you resolve very many cycles, let's say 4, 5, 6, 7, 10 cycles, when you only resolve 2 or 3, those are totally compatible in principle with the basically the AGN noise, because the AGN luminosity has a red noise, meaning that the oscillations that are longer time scale are more. So there is actually a work, it should be this one, that basically states that even just putting some AGN noise and looking for binaries in a synthetic catalog in which there are none, you can find them because of the just the fact that the low frequency power of the AGN spectra is higher, if it makes sense. So it's hard to make statements because we have candidates, but we don't know how many of them are real binaries. I would say that we need more than one way to really say this is a binary. So if we have a modulation on the light curve, it would be ideal to have a second test to really test the binary hypothesis. If the test is passed, then we can be way more sure. Right now, it's hard to say. I hope I more or less answered, or not answered, maybe.
Well, I'm just a little worried now. But I thought there were many more mergers that we usually see.
Oh,
I had not thought it was only 10. I
uh,
mean,
But that's just this kind of merger, right? There are other things in my understanding.
with
Well,
this,
it's all the noise are strange, right? So it'll be a pretty big black hole. Oh, that's okay. That's true. The long.
Because the waves in white water.
Uh,
And it's also going to see some southern mass black holes. Those also a couple.
It's the real focus I thought was
Yeah.
a massive black hole. That's why it was going to million.
Yeah, and it's extreme mass. Also. Yes.
Yeah.
So I think those should be open.
Yeah, so I'm not talking about extreme mass regime spirals, which by the way are something I'm also very interested in. But those are even more uncertain, I would say. But yeah, I think probably that the truth is in the middle, and tens of mergers, it's not such low number if you consider the fact that now we have nearly zero, I mean, solid candidates. We don't have, especially, I mean, the hierarchy universe, we don't have anything. So even just, I don't know, 3 Elisa mergers at redshift 6 of 10 to the 4 solar masses. This would be already huge. We won't be able to do impressive statistics, but it can give us something that for sure we don't have now. So my perception is that it's worth it. Then of course you can judge. But yeah.
But I agree with Chef. The impression that all of us have had is that Lisa is going to be kind of inundated with black hole mergers. In fact, the hard part may be even separating them out, and we're going to see, huge numbers. Now suddenly you're not facing 10, maybe it will be only 10. 10 is great, I agree. But somehow I think the community has been brainwashed into thinking that it'll be like LIGO. LIGO actually promised that in the future they will actually see the whole universe. But they're saying Lisa is not going to do that. We'll only see.
But LIGO will be over the bed before the next step.
Yeah, that's true. That's true. So, I mean, this will be good news at the end of the day. But yeah.
Yeah.
You can't really count on that. It's not big.
Well, it happened once. It'll happen again. Yeah.
Like I missed that day in the statistics course.
Yeah, final question.
Can we talk about gravitational memory?
Oh, okay. This I don't know. What do you mean with gravitational memory?
Well, there was a paper by Nick Foles last night.
Okay.
People talk about gravitational memory. They're hoping to measure it at idle in the next 5 to 10 minutes. It's the DC effect, the shift and displacement. And LIGO isn't very good at it because it's on a pendulum. The mirror's on a pendulum and they swing back and erase the memory, but you have to measure that. But other things like the binary pulsar array are sort of more suited because you check on it every few weeks, and so you don't have to see it in real time. You come back and see it. And I think that in a sense it's only been a few papers on it, but I think there's a sense that Elisa might be a good memory device because it is inertial, and so the shifts can be more easily measured.
Okay, well, it's a very interesting question. I have to admit my ignorance.
And
on
unlike
this,
this, it's very
actually.
easy to compute because it's a universal.
Okay,
There isn't very much uncertainty in how big that is.
okay, well, I will definitely look into it. It's very,
Well,
but I
there
don't.
was a paper but it's not the first one.
Okay.
I'm
Okay,
talking about going to
Sure.
So,
Thank you. Yeah, thank you so much. I mean, I don't know really what to add because I'm really not expert about this, but it seems interesting, so I'm definitely going to look into it. Thank you so much.
All right, we should probably conclude here. Thank you very much.
That was a great talk.